Welcome back. Okay, ladies and gentlemen, our speaker is a luminary in the field of semiconductor device physics with an sorry, with an illustrious career marked by achievement and passion for research and teaching. Dr. S.K. Masul Islam embodies the spirit of academic excellence. Dr. Islam is presently working as senior scientist CSR Siri and have completed PhD from IIT Kharagpur and Masters from Jadavpur University, West Bengal. Dr. Islam have numerous journal conference and book chapters with more than 300 citations. Dr. Islam research interests includes graphene electronics, sensor nanofabrications, semiconductor, nanostructures for photonic electronic. Without further delay, let us warmly welcome to the stage Dr. S.K. Masul Islam, who will be sharing valuable insights. Please, sir.
Very good morning, all of you present here, my respected faculty members and students. And thank you so much for your nice introduction. So today's session, the topic of the session is indium acid quantum dot in gallium acid MOS, that is metal oxide semiconductor, and graphene based devices, that is actually flexible devices for so many electronic applications. Basically, I have divided the talk into two parts. One is related to your gallium acid MOS, where I have embedded indium acid quantum dot, and another one is graphene based flexible electronics. Now, basically gallium arsenide is a 3,5 compound. Why 3,5? You see the periodic table, 3,5 is nothing but the group 3 element and group 5 element in the periodic table, right? Now, why scientists are more interested in case of your 3,5 semiconductor devices? Because it is comparatively stable material than the other sorts of material. As you can see here, band gap also varies with a wide range. You can also tune the band gap of the material by suitable alloy formation. Now, it also exhibits better emission and absorption property as well. Now, it can grow the material, means you can deposit or grow the material even in a very suitable manner onto the proper substrate. Now, in these devices, as I told in initially, that this is a gallium arsenide MOS, means gallium arsenide based metal oxide semiconductor devices. So here what I have used gallium arsenide as a substrate rather than channel material. Why gallium arsenide is proper substrate as a channel material? Because it exhibits so many advantages. What is that advantage? That advantage is high electron mobility, at least 5 times greater than your silicon. Silicon in 1800 semi-square per volt second, whereas for gallium arsenide it was 9800 semi-square per volt second. It also exhibits high breakdown field rather than low power consumption devices, and you can also apply this material for high speed device application. Now, there is a certain limitations of using gallium arsenide, okay, rather than your other sorts of material. What is these limitations or disadvantage? Because unlike silicon and SiO2, you see SiO2 on silicon, that SiO2 very stable material on silicon. But unlike SiO2 on silicon, it does not have any native oxide as well. That is your gallium oxide or arsenic oxide, but it is very poor native oxide on it. Because of this, there are very several phases as well, Za2O3, Za2O5, as well as for arsenic oxide As2O3, As2O5 also there. Because of this oxide formation, they are Fermi level is pinned when you are talking of the device. In case of, if you draw the band diagram, their Fermi level is pinned near the middle of the band gap. Means your Fermi level is not shifting even you dope the material in a suitable manner. So this Fermi level pinning at the interface between high-K dielectric and semiconductor greatly degrade your device performance. That's why what we need to do prior to the deposition of high-K dielectric or any kind of material, before processing or your device fabrication, you have to passivate your gallium arsenide substrate by suitable material. That is called your interface passivation layer. So what is there here? In the process succeeding side, I will tell you. Now, since it is a MOS devices, means metal, first of all metal is there, then oxide material, then in the bottom portion is your gallium arsenide. So their oxide is your dielectric. So why high-K dielectric is needed? You can see because of your greater capacitance as well. So if you see you see here two terms is there. This terms is constant and the oxide is directly proportional to K and T oxide. But if you increase the COX, if you want to increase the COX, rather you have to increase this one by, you have to decrease this one, but you cannot decrease this one too much. Why? If you thin the oxide thickness, if you try to thin the oxide thickness, in that case what will happen? That will actually, in that case your leakage current will be higher. That is unwanted. That's why only option is K. So you have to increase the K value. That is your high K dielectric constant. Now, again, I told you in the previous slide, you have to choose only high K dielectric, but you see here in the diagram, you cannot choose such a material which dielectric constant is too much high, because in that case what will happen? Your breakdown field also decreases. That is also you don't want. If you increase the dielectric constant, your breakdown field also decreases. In that case, as we are applying very little amount of voltage, your device will break down. So you have to choose a material in such a way so that your both properties will be fulfilled. Your means dielectric constant will be high, as well as the breakdown constant will be fulfilled. That's why in our case I have chosen ZrO2. In my cases I have used ZrO2 as a dielectric constant, as a oxide material. In that case you see dielectric constant also high, at 25, and your breakdown voltage is 3.8 megavolt per semi. Now I have choose the here the system is MOCVD, that is metal organic chemical vapor deposition technique. It is nothing but a technique by means of which your metal organic compound is deposited. Why metal organic? You see in the successive slide I will show you what is the advantage of MOCVD, because for research purpose people are using OND, MB or ALD. But for bulk production or industrial application, people are using MOCVD, because MOCVD facilitates bulk production of the devices. It also several advantages are there. Your not necessary your ultra high vacuum, you can also grow the material even in the atmospheric pressure, and it also facilitates very large area coverage, and even you can control the various thermodynamic reaction in a very suitable manner. Now, what is the typical reaction process? What is involved in the MOCVD? You see, first of all the precursor molecule. In my case, I have taken what? Indium arsenide. So, if you grow the indium arsenide, in this case, what is your precursor material? That is trimethyl indium. Why it is metal organic? You see, here only organic compound metal is there and metal is indium. So, both compound will be present here. That's why it is called metal organic compound. See, metal organic. Now CVD. CVD is nothing but the chemical vapor deposition technique. All the chemical material by means of arsine will be actually transported into the reaction chamber by a suitable carrier gas, that is in your case hydrogen. So hydrogen will carry this one and this one into the reaction chamber. That reaction will take place. Indium will combine with arsenic, and another byproduct is your methane that is vent out to the scrubber system. Suppose you want to grow the gallium arsenide. Here I have used indium arsenide. Suppose you want to grow the gallium arsenide. So in that case what will happen? You need to take trimethyl gallium plus arsine equals to gallium arsenide plus methane. Suppose you want to grow gallium phosphide. So what you need to take? You need to take here trimethyl gallium plus something your arsenic phosphine pH3. Instead of arsine you have to use pH3. So in that case indium phosphide or gallium phosphide will be there. Understood? So this compound basically combination of your organic compound as well as the metal compound. That's why it is called metal organic compound. Now growth of indium arsenide. Through the literature survey I have seen that people are generally using high temperature for this growth technique. Okay, it is related to your 500 in most of the cases 500 to 600 degree centigrade. And in case of indium arsenide quantum dot, the electrons are confined in 3 dimensions, and it follows the Stansky transform growth mode. When and in this growth mode, what happens? You know, initially what this is what actually when we are talking about your Stansky, several growth mode is there. This is actually related to your epitaxy, thin film epitaxy. Okay, one is your Stansky construct growth mode, another one is Volmar-Albert, and another is Frank van der Marwijk growth. Hence, what happens, you know, in this growth mode, at a certain critical thickness, initially your 2D thin film will be grown. So that 2D thin film into the high stress actually, that's grown 2D thin film actually is in the high stress, and after relaxation or minimization of surface energy, that thin films will be actually relaxed into 3D islands, that is actually 3D quantum dots. Hence, by forming these quantum dots, the strain will be relaxed and total energy system will be reduced or minimized. Now, limitations of the high temperature growth. As you know, most of the cases people are growing at high temperature, but at high temperature, the size of the quantum dot is getting bigger, and your quantum dot size, if size of the quantum dots, suppose quantum dots are distributed in the surface, if size gets bigger, then it will coagulate in some way. Eventually, your quantum confinement effect will be lost, and it also assists your thermal arc diffusion as well. It also prevents the formation of SAR interface, which also facilitates the degradation of the crystal quality. Sometimes it may dope the material even. And eventually what happens, you know, charge loss is taking place from the bigger quantum dots. So that also will be give your greatly degrade device retention characteristics in case of when you are talking or fabricating your non-volatile memory devices. Now, through literature survey, you can also see instead of using quantum dot as a charge storing element, you see again I am telling I have used this quantum dot as a charge storing element because you are talking about MOS devices for non-volatile flash memory application, right? So there should be some material or in terms of nanomaterial, nanocrystal or in a quantum dot, people are using previously metal nanoparticle, silver nanoparticle, gold nanoparticle, something like that. But use of silver nanoparticle leads to several difficulties. What is that difficulty? In that case, metal, because oxide metal is there, metal oxide semiconductor, oxide metal is there, that oxide will react with the metal compound, metal nanoparticle. In some cases, metal also acts as a dopant in case of source and drain region. Again, you know, synthesis of stable nanoparticle is a very cumbersome job. It does not fit process lines of the device manufacturing technology. What does it mean? It does mean that in my cases, by using MOCVD, my whole purpose is fulfilled. But in case of metal nanoparticle, you have to pick up the substrate into the different places separately so that you can synthesize your nanoparticle here. But in case of Indian arsenic quantum dot, that system, it can be grown in the MOCVD system as well. You no need to pick up the material outside of the MOCVD system. Now, the motivation of the, I told you, so many cases, previous literature you can found, so many reports are available in the literature where most of the cases your growth has been taken place in 500 degree C to 600 degree. Okay, and people are using also nanoparticle, but instead of using nanoparticle, I have used semiconductor quantum dots, that is indium arsenic quantum dot as a charge storing element. Why? It exhibits so many advantages, that is high excited binding energy, formation of many bands as large discrete density of state. Because whenever you go to bulk to nano, so many discrete energy levels are created that will actually responsible for storing your charges, right? That storing your charges actually finally resulting your capacitance. Now, quantum dots also favor low leakage, low voltage operation and low power consumption, and in this case, enhanced data retention or enhanced or increased capacitance will be fulfilled. And you can see there, in case of nanoparticle, formation of stable nanoparticle is very difficult task, but epithelial silicon quantum dot is considered to be very pure. Now you see, now first of all I will talk about the growth of the material. Growth of the which material? Growth of the indium arsenic quantum dot on gallium arsenic substrate, as well as when we are going to your capacitor or MOS capacitor, then we have to grow this indium arsenic quantum dot on dielectric substrate as well. So these are the typical growth parameters. You see, growth temperature I have taken 300 degree centigrade to 530 degree centigrade, but in literature you can found people are using more than that temperature, and growth duration is this, and this is actually precursor material. You see, that is your actually trimethyl indium, that is precursor material, because you need to grow what? Indium arsenide and arsine as well as there, and this hydrogen will act as a carrier gas. This hydrogen carrier gas will flow this and this into the reaction chamber. This is actually reaction chamber of the typical MOCVD system. Okay, all the parameters will be controlled in the PC. Okay, you have to set this flow parameter, growth temperature and growth duration. This hydrogen carrier gas will carry this one and this one into the reaction chamber, and these two material will react, and finally it will form indium arsenide, and the byproduct you will found is the methane, and that methyl here in the back portion, so many vent system is there into atmosphere. It will react onto the charcoal bed, and there, that your methane will be actually vent out into the atmosphere. Okay, now you see this is the AFM images. AFM image is what? Atomic force microscopy images. Okay, atomic force microscopy images of the indium arsenide quantum dot on gallium arsenide substrate. You see, this is actually 380°, this is actually 400°, this is 450°, and your last one is your 530° centigrade. You can see, apparently you can see here, when your temperature increases actually from 300°, 380° centigrade to 5° centigrade, 530° centigrade, in that case with increasing the temperature, your size of the quantum dot get increases. Okay. Why? I will tell you in the later slide. Again, you can see here the TEM images, a transmission electron microscopy. Okay, you see several bright spot pattern is there. That spot is actually your formation of quantum dots, and you can see this is actually SEDD pattern of the quantum dot. SEDD means selected area electron diffraction. You can see bright spot pattern is nothing but your quantum dot, which will actually ensure the single crystalline growth of the indium arsenide quantum dot. And you can see here so many lattice fringes are there, that you can calculate or determine the interplanar spacing, which is found to be 2.94 angstrom in my cases. You see, this is the tabular format of the several parameters of the formed or growth your indium arsenide quantum dot. When you are increasing temperature from 380 to 5 degrees C, your size of the quantum dot, rather the diameter of the quantum dot gets increases, while density decreases. Why? Because when you increase the temperature, that your atom molecules, that is precursor molecule, or your atom molecule, that is indium and your methyl becomes more mobile. Okay, then in that case very rapid nucleation process will form. That naked nucleation process will lead to the with basically resulting your bigger crystal size. Okay, and in that case when size getting bigger, in that case in increasing temperature, so many quantum dots get agglomerate, and in that case your quantum dot density also will get decreases. Now this is the AFM images of the indium arsenide quantum dot, which is grown into the dielectric material. This is not into the gallium arsenide. This is the formation of indium arsenide quantum dot on dielectric, that is ZrO2. Okay, you can see that is your 550° centigrade, 500, 550° and 580. Yeah, but in that case, because you are growing the material into dielectric, that will actually follow direct alignment or Volmer-Weber growth mode. Okay, in previous cases it is would follow the Stransky constant of growth mode. Okay, but in that case the growth procedure will follow Volmer direct ionic formation. Okay, but in this case when you are increasing temperature also, in that case also your size of the quantum dot gets increases, and it is the corresponding your AFM image. This is 500°, this is 550°, and last one is the 580°, and that is actually HRTM image of the quantum dot. Okay, this one you see, and so many lattice fringes is also there. And again you can see the from AFM images the size of the quantum dot 5, when increasing temperature size get increases, in TEM also. But here one confusion may be rise, sir, you are saying that for AFM images size gets bigger rather than your TEM images. Why? You can see, because in case of AFM images, when actually this is actually tip actually. When you raster scan the surface, then this tip image, that tip cannot follow this manner. Your tip actually following this manner, right? It cannot penetrate this region. Whenever you raster scan the surface of the quantum dot, it actually following this path, not this path. Okay, not this path. That's why the apparent size of the, you are getting this size, not this size. That's why, because in this case what you need to do, you need to actually convolute your peak size, tip size. Okay, that's why in case of AFM your particle size is quite high rather than your TEM images. Now as we are telling that set quantum dot you are basically growing quantum dot. But what is the size of the quantum dot? Because in that case your particle size will be at least comparable to your excitonic Bohr radius. That's why I have calculated the size of the quantum dot. In that case, excitonic Bohr radius of what? All this one is the formula actually. Okay, all the value I have put there. If you calculate, if you determine the value, actually excitonic Bohr radius of indium arsenide is 36 nanometer. From this value, you can conclude that the size of the particle at least should be this or lower this one. You can tell that if the size of the particle or indium acid particle is 36 nanometer or below 36 nanometer, then you can say that your formation of the particle is the actually nothing but your quantum region. Okay, but in our previous cases you have seen the size of the particle in which range, 5 to 18 nanometer, so that is virtually less than 36 nanometer, so you can say that the formation of quantum dot actually happened. Now to ensure the formation of the material, in our case it is the indium arsenide. So what is that? Indium also present and arsenic will be also present. For indium, that is actually orbital splitting. For indium it is 3d 5 by 2 and 3d 3 by 2. Two possible orbital formation is there. So you can, the very distinct peaks are there. So you can also see that, show you can determine that in that case indium also formation was taking place, and in this case arsenic, you see this peaks is corresponding to the arsenic indium, that is 41.4 is electron volt, and that peak is responsible for, if you see the file that is actually presence of indium arsenide. So you can say that your formation of metal is nothing but your indium arsenide, and in that case, because there are so many oxygen may be oxidized, but the peak of the oxidized arsenic oxide very low, so you can say that very less amount of defect is present. Now ZrO2, this is actually X-ray photoelectron spectra of ZrO2. You can see that for ZrO2 also Zr3d 5 by 2 and Zr3d 3 by 2, two slots of your orbital splitting taking place, that is also responsible, and this is the oxygen. You see 532.1 liter was responsible for the formation of this distinct peaks. That, so this is Zr and this is O. So by combining this one, actually ZrO2 formation is taking place, which is nothing but your ZrO2 only. Now I am going to your device fabrication part, that is actually gallium acid MOS. So first of all, you have to take this gallium acid, you have to clean this one. This is actually decreased by acetone, methanol. These are all related to your device material processing as well. The acetone, methanol, then it is base pyranol solution is there. One is because of removal of native oxide and element of arsenide, then rinse with denatured water. Finally, you have to dry it into the nitrogen gun. Okay. Again, I have to see, prior to the deposition of anything, any layer, you have to passivate the surface in order to minimize the interface trap charge density. What is that in our case? Gallium phosphide passivation layer I have taken. Okay, that is 1.18 or 1.8 nanometer only to minimize your surface stress only. I told you, unlike SiO2 on a silicon, here no formation of stable native oxide there. In that case, so many surface stress is there. So to minimize the surface stress, to minimize your device performance, increase your device performance, prior to the deposition of any dielectric layer, I have deposited gallium phosphide in gallium arsenide. You see, then I have deposited ZrO2. Then I have deposited the growth of indium acid quantum dot. You see, so many materials are for zirconium tertiary butoxide and oxygen is there, and these two material will react into the chamber, and finally it will be growing the ZrO2. After that, your ZrO2, you see here international quantum dot 5, 20 bar, 12.5 and 16 nanometer are grown on tunneling ZrO2. Okay, you see here, this is the actually picture. First of all, this one, then gallium interpassivation layer, then this is one your ZrO2, this is your formation of quantum dot, this is general control ZrO2. Why this is taking place? Because see, if you are putting the bias potential in two sides, in that case to minimize your leakage current only, so that electron cannot escape into this region, because here actually electron storage is taking place, so that this the deposition of this layer actually ensures the, so that electron leakage current will be minimized. That's why control ZrO2, that thickness is too much rather than this. This is in the range of your 5 nanometer, this is in the range of 23 nanometer, right? And you see the all the successive layers are present there in cross sectional HRTM images. this is gallium arsenide, this is gallium phosphide, all the layer by layer presents. So these also ensure the formation of the structure. Now by capacitance voltage measurement 100 kilowatt, you see so many your interface, your hysteresis width is found. In that case, you have sweep the voltage whenever minus 10 voltage to 10 voltage is actually, and the maximum memory window you found is your 6.8 or something like that, 6.07. Okay, you see whenever you swing the voltage from this 10 minus 10 to 10, your memory window is found. That is actually this memory window responsible to store of the charges. And in case of here where no quantum dots are present, you see very less negligible memory width here obtained, because no storing element is there, no such element is there which is responsible for storing the charges. This where very low hysteresis width is found here. And again I told you that even if I minimize or passivate the surface with gallium arsenide surface passivation layer, in that case you see some little amount of interface trap charge also already present. But to ensure whether it is caused by your quantum dot, whether your storing of the charges, this hysteresis width is due to what? Whether it is intimacy in quantum dot or it is due to the interface trap charge density. For that purpose, I have already characterized the device frequency dependent CV characteristics from, because in this case I have swept the frequency from 10 kilohertz to 1 megahertz. If you sweep the frequency, in that cases also you see no frequency dispersion is found with almost constant memory is found. So this will ensure, because at low frequency you see low frequency actually your interface trap density will be actually respond. But if we increase the frequency from 10 to the at higher frequency, it cannot respond. But you see at 10 kilohertz as well, for all the cases your no much dispersion is there. So this actually confirmed it is that the hysteresis width is due to the quantum dot, not due to the surface state or interface trap charge density. Right. Now this is your current IV characteristic, or rather your current density versus voltage characteristics, which actually confirms the leakage current density. You see at -1 volt, a leakage current will be very significantly very less. Okay, that also you ensure that your device is very good. No such your significant leakage current is there. Now you see programming state. When I am applying the potential here, electron will come into the, this is actually ZRO2. By surmounting this barrier, electron from this side will come into this side. That's actually responsible for storing the charges here for some time. That will actually programming state. Okay, with applying the positive potential here, all the electron will come out from this side. Okay, positive potential here, electron will coming into this side, and here in the surface your discrete energy state is there, that is interquantum dot. Electron will spend some time here. That is actually responsible for your electron storage. When you are applying negative potential here, then all the storage electrons into this region will escape from this side. Okay, escape into this side. That is actually leading to your erasing operation. Okay. Now this is the corresponding energy band diagram of the devices. Okay, that is gallium arsenide, this is channel ZR2. All the value I have taken in the standard literature, and this is actually indium arsenide quantum dot. All the corresponding value of the electron affinity, your band gap, I have taken from the literature. Now this is the charge retention as well as your endurance characteristics of the devices. You see, whenever you are in this case, almost 90% charge, that is actually quite good. Almost 90% charge retention is happening in the case of these devices even after 10 to the power 5 seconds. Okay, almost 1 day. Okay. Now for this is the endurance characteristic. You see after 10 to the power 2, up to 10 to the power 2 programming cycle, your device actually leads to very stable. Okay, no such degradation is there, very linear is there. But after 10 to the power 2 cycle, okay, you see slight difference is there, slight degradation is there, slight lower. So how much this one? If you calculate the shifting of the field band voltage, that is also very negligible, 0.18 electron volt. Okay, that also ensure that no much shifting or no much device degradation, very stable characteristics you can found in case of these devices. Now by varying the size, now I am taking about the what is the effect of size on the capacitance variation. Okay, you see with increasing the size of the quantum dots, with increasing the size of the quantum dots, you can see the memory window also with increasing memory d charge density. If you increase the size, in that case your charge density of charge will be decreases. In that case your memory window also be high. This is actually room temperature high frequency operation of the CB voltage. Okay, this is size of the quantum dot. If you increase the size, that is your inversely proportional of the charge storage. Okay, in case of increasing the size, charge storage will be getting, that charge storage is related to your memory window. So with this one again with another plot is also there, frequency dependent. I again told you that is actually room temperature frequency dependent to ensure that whether it is due to your internal quantum dot or whether it is your interface type charge density. Again frequency varied from 5 kHz to 1 MHz, and in that case, in all the cases, means your no such frequency dispersion will take place. So you can say that all the cases your charge storage is due to the indium oscillator quantum dot, not due to the trap charge density. Now again for all the cases you can see here all the charge retention taking place for all the devices 5 to your 16.5 nano. Charge retention into the quantum dot get enhanced with increasing the size of the quantum dots. Now leakage current density. To analyze the leakage current into the devices, I have formulated three kind of devices. That is your aluminium Z2 to gallium, that is MOS, and again in this case surface passivation is there, no quantum dot is present, but finally in these devices, okay, where your interface passivation is layer is there as well as interface your quantum dot also there. Okay, three kind of devices you see. In these are the two these are the three devices corresponding gallium arsenide Z2, and it is your metal. Okay, this is your second devices, this is your third devices, where as your both are present gallium arsenide passivation layer and as well as your interface quantum dots are present. In this you see, in case of your passivation layer where you have passivate the surface, in that cases your leakage current density gets lower, but in case of your unpassivated surface, this is this one, in that case you see leakage current gets higher, because if you whenever you applying your passivation layer or depositing your passivation layer, in that case it can actually passivate the surface. So in that case less interface state density present there, but in case of unpassivated surface your no such your significantly higher number of surface states is there, that is actually responsible for your high leakage current density. Now this is the IP characteristics in several kinds of three kinds of devices. You see for first devices where only Z2 is there, that is actually follows pole Frankel emission. You just plot this in pole Frankel emission. This is the all the corresponding formula, and this one your passivated surface follows your pole Frankel emission. Okay. And this is your final device, quantum dot enabled device. In quantum dot enabled devices, I told you this is your leakage current density 10 to the power minus 6 actually, and in that case your current follows Fowler-Noddahm tunneling mechanism. Now conclusion, I can say that growth of indium arsenide as well as gallium arsenide substrate as well as high K dielectric present, and in that case the maximum memory window find is 6.83 and your very low leakage current density this one, and your charge retention around I told you 90%, and I also investigated the size quantization, this effect of size on the quantum dot, and I also analyzed the leakage current density in three kinds of devices. Now this is another chapter I have to do, that is actually synthesis graphene based flexible devices. Okay, now this is all the derivative of how graphite is this is actually graphite flakes. This graphite preparation of graphene by electrochemical exploration technique. See, graphite flakes are there, that graphite sits into the electrolyte solution, dipped into the electrolyte solution, then voltage potential apply here, then that graphite flakes turned into your filter paper. Okay, then it will actually whole night it is actually in black to solution dipping, then ultrasonication taking place. If after ultrasonication it will be formed into the from flake formed into the liquid graphene. That graphene actually used for your device fabrication technique. Now this is actually fabrication of flexible substrate. You see PD flexible. What is the flexible substrate? That is actually flexible PDMS substrate, polydimethyl siloxane. So this is silicon elastomer is taking place. You see that is actually taking with the cleaning agent 10:1 ratio. You put into the Teflon board. Silicon Teflon board is there. Solution is to drop casted into the wafer substrate. Okay, and 80 degrees centigrade, that is the baking temperature. apply, then you peel off the substrate from the surface, you see, you just peel off and finally you get this one. This is actually flexible, bendable, rollable, right. Now you see you have to transfer this one into the graphene, okay. Now this is black portion is actually graphene, and in the bottom portion you see the actually flexible PDMS substrate. You see this one into the, when no stress is applied, by when your strain is applied, you can stretch the material into this region. Actually this stretchability you found is 65% in this case. Now the analysis of graphene by your Raman analysis, this is actually for material conformation test. You see so many peaks are present, D band, G band and corresponding to D band. This peaks is actually ensure that your metal is nothing but the graphene, and this is your corresponding FECM images of the graphene. Now these are the devices where graphene based flexible sensor we have fabricated, and in several substrate. This one, first one is your flexible PDMS substrate, second one is PET substrate, third one is your polyimide PI substrate, and fourth one is your carbon fiber. In all the cases you see, whenever you are testing the devices, in all the cases you are applying pressure or strain or applied external forces, you see in all the cases your resistivity change in resistivity is taking place. That change in resistivity actually your response actually is gauge factor. Okay, so you can see that in all the cases your graphene is used as a sensing element. So this you see, whenever you mount the device into a wrist, actually you mount the devices into a wrist in all the cases by your pulse, because in the wrist your pulse sensation is there, you actually sensing the devices. In all the cases your change in resistance is found, that is actually proves that your device is quite sensible. Now another investigation is also there, where in so many nanocomposites we have formed. What is that? Silver nano, that is silver nanoparticle, multiple carbon nanotube and PDMS, as well as GNP, PDMS, and in all the cases I have used flexible substrate as PDMS. And another one is silver nanoparticle, graphene nanoplatelets, and in all the cases, okay. This one is the first one, this one is the second one, GNP, PDMS, and third one is in the GNP along with PDMS, along with silver nanoparticle onto the PDMS substrate. And this is your material conformation test, okay. This is XRD measurement, okay. In all the cases you see, first one is silver, presence of silver nanoparticle is there, and second one is GNP is there, the peak of GNP is found, and the third case is as well as your silver along with your GNP, you can also find so many distinct and large intensity peak of silver, okay. And this one is your Raman spectroscopy measurement, okay, for all the cases for material conformation as well, okay. D, G and 2D bands, in all the cases he found D, G and 2D band. Because of this appearance of this peak, you can ensure that formation of graphene and GNP is taking place here, okay. Now this is your device fabrication, your device testing. You see, when applying strain, in this case you found gauge factor. Gauge factor is nothing but your change in resistivity upon applied pressure, right? Change in resistivity delta R by R divided by applied strain, okay. Gauge factor 188, this is one 184, 104, 184 something like that, and this is 221. So highest gauge factor you can achieve in case of silver nanoparticle and GNP based devices. So you can say that this device actually showing best result. So in that case your this third one is your very suitable devices or best devices. Now whenever you mounting the devices into your bright, that is the breathing analysis. You see, this is actually your devices when you are mounting into your mouth. Whenever you deep breathing is taking place, in that case change in resistivity your high, but whenever your normal breathing takes place, in that case your change in resistivity is quite low. That also ensure that each device is very sensible, okay. In that case also see GNP PDMS case, but you see very your prominent peak is there in case of here silver nanoparticle GNP. In that case you see your into the change in resistivity also gets higher, and whenever your normal breathing is taking place, in that case also your device is sensing. Now this is also your response times measurement. You see in this case in 3 plots for first devices you have achieved 5, but in this case this is very high, but response times is too much low here, 130 milliseconds. So that your superior characteristic you can find here. So you can say that this device is actually your best devices as compared to your other 2 devices. Now this is another research where we have fabricated solar cell using graphene and polymer. What is that polymer? Instead of graphene we have used PEDOT-PSS as a and MHPPP as a polymer substrate. PEDOT-PSS is responsible for whole transporting layer and MHPPP is a photoactive layer. And you see very significant result we found. In that case is also your field factor 56 nanometer, and even if very low, but you can ensure that this structure of the material ensures the formation of solar cell. Now this is another solar cell structure of the another investigation related to your solar cell devices, where we have used graphene as your cadmium sulfide, okay, to ensure the efficacy of cadmium sulfide as a protective layer. You see in that case also you can get fill factor in terms of your 56.5 fold efficiency is quite low, but in that case your current density and your reverse saturation kind of identity factor also significant. That's why you can use this material as a suitable application in solar cell devices. Now this is actually design of the photonic crystal based devices for biosensing application. Now you can see this is the SOI substrate, silicon dioxide, and this is another upper silicon layer or device layer. The silicon substrate is patterned in such a way so that your photonic band gap, you can achieve the photonic band gap in this region. So by simulating the device, we have found that the lattice constant should be 200 nanometer and the hole diameter should be 120 nanometer. You have to tune or you have to optimize the device in such a way so that upon applying your incidenting light, your reflectivity or wavelength should be in this region, photonic band gap region. You see, in that case also your variation of hole diameter, this is actually an wavelength you can found in these cases into the photonic band gap region. Now you see this is the reflecting characteristics of the devices, and the sensitivity of the devices of the found in 91 nanometer by refractive index unit, when you are varying the refractive index actually 1.1 to 1.4. Okay, the main idea is that whenever you are patterning the surface or you are applying some kinds of your analyte or biomolecules, that is actually change in refractive index taking place onto the surface. Okay, surface refractive index will get changed. That reflective change in surface refractive index will actually lead to the shifting wavelength. Now another focus is also there to your component should be smartphone integration, so that this is actually just hardware kind of things. So many we have purchased so many things and assembled in such a manner so that actually light this is a pinhole, this is CMOS camera, collimator, all the arrangements is there for actually smartphone integration. We are getting this one. Now this is another kind of design of the LED actually. LED is nothing but your light emitting devices. By applying the suitable potential between the positive and cathode and anode, the nothing but your emission of light when you are talking or taking the direct band gap material. That is actually gallium nitride based material. You see, this is the simulation structure, all the parameters you have taken this one, electron mobility, hole mobility, and this one actually simulation parameter as well. This is the structure of material, okay, and this one is actually emitting UV light, and you see UVC region, that is actually 266 nanometer. In that cases you peak, so if your peak in this region, so that is UVC region is achieved. Now this is interface internal quantum efficiency 25% is there, turn on voltage is achieved 5.2 voltage, and in there the two cases output power is there, both two electrode, where finger electrode is taking, that is power in the range of 4.9 milliwatt, and when you are taking electrode in the circular pattern, in that cases your power output power will be quite high. Now this is another devices where UVB should be achieved. Now this is the corresponding structure, and all the simulation parameters has been represented in tabular format. Now you see the UVB 295 actually falling into UVB region, and all the corresponding related to your interface internal quantum efficiency, your output power in taking into the your circular pattern electrode as well as your finger electrode we have determined. Now this is another structure where we have this is not cyber, the copper strip has been taking is a heat sink. So many copper strips are there. Okay, this one, and this is actually we are, you see all the LED has been situated here, and you see upon putting the LED, if you see the potential, all the 5 LED are in series and 3 strips are in parallel combination. You see upon applying the potential here, all the LEDs are glowing. So means that your device fabrication is suitably taken place. Now you see this is my publication, all my publication throughout my career, this one, all the peer reviewed international journals. Now you can see, and these are the book chapters recently published. This is the conferences I have attended. Now thank you so much for your kind attention, and now I will be happy to answer if any question is there.
Sir, hello, sir. Question is, my question is regarding epitaxial layer growth. When we like change the temperature of a chamber, so what is a change in a growth?
See, temperature is very important. This is the crucial factor. When you change the temperature from this to this, you see when the change in temperature, see, I told you metal organic compounds, trimethyl allium or gallium. When you change in temperature and taking place, getting from lower to higher, in that case, your adatom molecule, what is that adatom? Indium, arsenic, methyl, that becomes more mobile. Okay, if your adatom molecule becomes more mobile, in that case, what happens? Your rapid nucleation process will be happen. Means your rapid growth will be, rapid reaction will actually happen. That rapid reaction actually, why? Because of this rapid reaction, instead of your formation of quantum dot, your thin film will be deposited. Okay, that is the thing actually.
One more thing, sir. So when we AFM is there, so there are some defective states are there. So how we identify that in a AFM? So which one is a defective state?
See, from AFM we are not confirmly say that it is defect or not. AFM actually your surface topology. Okay, surface morphology for identification. From AFM you can determine the surface morphology, surface topology, surface roughness as well, and actually here surface your particle size also. Okay, that is actually for the determination of particle size, and your defect traits is determined from another study that I have not undertaken here. That is also another study you have to, I told you na, actually gallium arsenide surface is too much rich in surface state is there, right? So that is actually I did not undertake because that much facility, that is actually determined by your DLTS. What is that DLTS? Deep level transient spectroscopy. That is actually confirmatory test of your tap states or interface type charge density. But here frequency dependent. Why? Because at low frequency, whenever we are applying low frequency, in that case if there are some, you see, no device is free from any interface type charge. Something little amount of your interface type charge must be there. Okay, that's why what I have done, frequency dependent measurement. If you are varying the frequency from low to high, but if some amount of little amount of interface tap is there, it must respond with low frequency. But if you increase the frequency very high, in that case it is lower. But even if I apply low frequency, in that case also no such dispersion is there. No such dispersion means no such shift in flat band voltage is there. That is confirm your less amount of interface type charge density. But actual determination, the amount, whether per semi square, what amount of charge is there, that is actually determined by DLTS, deep level transient spectroscopy measurement.
One more thing, sir. There is an Raman is there.
Raman measurement.
So sometimes there are two peaks are there. To how to identify that which one is 2D? Like, it's in your slide also. Sometimes double peak is there. So how we will identify that which one is 2D?
Acha. See, how, see, there are already range is there. one is your 1500 something, another is 1700, okay. But it should be means plus minus something, not much less than that or not much bigger than that actually. But you just remember that one D actually responds for presence of defect state. On G all not characteristic menu stretching vibration, and 2D actually number of graphene. So many layers are there, na. See, graphene means what? Single layer. Okay, maybe your CNT is there, so many graphenes are rolled there. Okay, so whether it is stacked layer, that is actually determined to ID by 2D, your intensity of 2D by Ig actually. If it is greater than 1 or greater than 2, it should be means multi-layer is there.
Thank you, sir.
You have shown that. Hello. Good morning. I am Dr. Rohit Goyal from TIT&S Bhiwani. Sir, I have one question. You have shown that slide on frequency dependent CV characteristics.
G.
And in that you have shown the maximum frequency is 1 megahertz. So can we increase that frequency to gigahertz range also? Like these days, most of the devices which are formed are in gigahertz range.
Achha.
Like whether you are talking of any device, amplifier or mixer or any other device, we are talking in terms of gigahertz range.
Achha.
And even for CMOS design also, if you are talking of combinational circuit or memory, we are mainly talking in terms of gigahertz range. So if we are taking this frequency dependent curve up to 1 megahertz, so whether it will be feasible to implement it in gigahertz range also?
In that case, I did not undertake in on gigahertz range because see, it also depends on the mobility of electron as well, how it can sustain. Okay, in that case, I have doubt whether it will take that much of frequency. Anyway, this will actually for application in very high frequency devices as well. But I cannot because I did not take, because for confirmatory up to 1 megahertz it is sufficient for this structure. 1 gigahertz I have also device that I have to check actually, but in that case, for very high frequency, if you need whether it will actually sustaining in that range, you have to perform the experiment.
Actually, also one more thing is there. Like if we go after the megahertz range, in that case the capacitive effects on the MOS will come.
Yes.
That is the most important.
Most important thing. Yes, correct.
So that's why I was asking.
That is actually high frequency application. I understood.
Thank you, sir.
Once again, thank you so much for giving me an opportunity in BKPIT. I just remain thankful to the organizers, basically, particularly Rajesh and the director sir, for giving me the opportunity to share some of my research work. Thank you so once again.
Thank you, sir. Now I will request FDP coordinator Mr. Rajesh Singh Shekhawat to provide a token of love to Dr. Islam.